Mr. Molikash, your friendly neighborhood calculus teacher. It's a joy to be back with you this week. We've made it through the first week of class. One down, 15 to go. I'm recording on my Mac now, so I've got some new stuff. I have a video camera, I have a writing tablet, and all that entails the stuff that goes along with the Mac. So this is the first video that I'm going to shoot on Macintosh. I was using another computer and another software last week. So anyway, having said that, I'm hoping that you have seen in Blackboard the pacing guide for this course and that you're following along like you know what's coming. Even if you don't understand all of these topics and what they even mean. This actually is spelled wrong, Riemann. But anyway, there's a long list of stuff that you're supposed to learn in your first calculus course, and these first 5 chapters of this textbook. We're going to take a considerable amount of time this week and next week and kind of finish off chapter 1, which basically has to do with the idea of limits. We looked at limits last week informally, basically by looking at a table of values, by looking at what happens on either side of an x value on a graph. We kind of started exploring the notion of continuity and those kinds of things. So we're going to kind of nail those things down a little bit more tightly. In this video, I want to talk to you a little about these topics: continuity, the tangent line, one-sided limits, limits at infinity. And what I'd like to do is I'd like to kind of go through, sort of talk through the textbook, okay? Now, at the end of this video, you have some suggested homework problems in this textbook to work through. Solutions are in this book. You just have to scroll down a little bit to see the solutions to selected problems. And the there's labs almost every week in this class. And so you should be working on the first lab for this week, and you should have, hopefully you've done the respondents practice test by now. Just kind of wanted to talk to you a little bit about the pacing. Now, I understand also that last week's video was really long. I mean, it was really long, like 45 minutes. I'm so sorry about that. So hopefully this one won't be as long, but man, I got a lot to talk about. So without any further ado, let's get into the math here. So the definition of the limit of a function, like what is that? There's a bunch of stuff that you're going to see in this book that looks really confusing. And by the way, the very first thing you should do is read. Right? Go read the text. If you haven't done that, you need to go back and kind of just read through, at least very quickly, just read through section 1.2 and 1.3. It will help you tremendously when you're watching this video. It will make a whole lot more sense if you've already skimmed at least through the text and you've pre-read. Okay, so read and then come back and watch this video, right, and then reread the section. Okay, I think it's going to be important to do those 3 things as we get going in this class, especially because you've chosen to take it asynchronously online, right? All right. So the book starts off in this section 1.2 talking about the definition of a limit that captures a certain property, right? And the property that we talked about is that as x approaches this x0 from either side, as values of x approach on either side here, that what happens is x closes in on that value. We're hoping, if a limit exists, that y closes in on this value, right? So what we would kind of ascertain from this picture, that is a problem. Let's try that again. All right, so what we're going to hopefully take away from this picture, headphone cable got caught, okay, got in the way. Sorry about that. Hopefully what we're taking away from this picture is that the limit of our function as x approaches x0 or x sub 0, sometimes you'll see people call this x naught of our function f of x, which takes on a bunch of different y values, is f of x sub 0. And we're going to find out later on in this video that when this kind of thing happens, that this function over here is called a continuous function. Okay, so keep that back in the back of your mind when we go down a little bit. Okay. So what does that really mean, like formally, in a definition when we write this down? Okay, what we're saying is that there is some value called epsilon. Suppose we want to require that the values of f of x differ in absolute value from this by some small positive constant, traditionally called epsilon. So this Greek letter is called epsilon. And what we require is that the difference between f of x, any value of f of x, and f evaluated at x sub 0, that the distance between those two things, the positive distance, is less than this epsilon. Okay, that's what they're saying here. And that when this happens, this is due to the fact that the difference between x and x sub 0 is less than some other very small number called delta. And I have to practice writing my deltas down. So let me try that again. Okay, a delta is kind of like a fancy D, right? It sort of looks like a musical note or that kind of thing, but it's tough. I don't know Greek that well. I just know what it's called. I know it's called delta. All right, so anyway, we readily see that this inequality is true for values of x lying inside the vertical blue box, right? So we have a horizontal blue box here. That's what this statement is saying. And then we have, let's see if I can use my mouse to scroll this down. We've got a vertical purple box, if you will, right here, right? So when x is in the purple box, we're hoping that y is in the blue box. That is the most simple explanation I can give you for this epsilon delta business, right? So this purple, it looks purple on my screen. Hopefully it comes out purple on yours. But this is sort of like a light blue here, and this is sort of like a lavender color. Okay. All right. So this observation, if x satisfies this inequality, if x is very, very close to x0 within an absolute value of delta, right? So this distance right here, this distance from here to there, didn't mean to do that. That distance from there to there is delta, right? That distance from here to here is epsilon. So within a radius of epsilon from f of x, we should see f of x sub 0. Actually I said that backwards. Within a radius of epsilon of f of x sub 0, we should see the values of f of x. So that is a very quick rundown of the formal way of defining a limit. Okay, a formal way, the very rigorous way of doing this. And this kind of thing is really explored more deeply in higher level math. So if you go on and take math in graduate school, if you look at the theory behind calculus, you'll talk about this in greater detail. We are not really going to explore questions having to do with epsilon and delta in our class. But I do owe it to you to tell you, Yeah, it does work. I was just making sure my keyboard still worked. I do owe it to you to tell you about this just in case you're moving up into Calculus 2 and Calculus 3. Okay? All right. So this is something that we introduced last week, and now we have a little bit greater understanding that when we are writing this down, we're saying that if x is within a very tiny amount of distance from x sub 0, that we expect y to be in a very tiny distance of f of x sub 0. So this picture is really worth a lot of explanation, right? Is wrapped up in that picture. All right, so there's some theorems on limits, and I'm just going to kind of talk through these instead of writing them out. The limit of a sum or difference is the sum of the limits. So, for example, let's just see if this works without me messing up. So, for example, let's say that you want the limit as x approaches 3 of x plus x squared plus x cubed. Right? Okay, technically this is the limit as x approaches 3 of x plus the limit as x approaches 3 of, there we go again, this little tool I'm using has got a little hiccup on it, doesn't it? Sorry about that. So maybe you can predict what I'm going to write down, right? I think actually there's supposed to be on the heel, I think there's supposed to be like a glove or something that I'm supposed to use to do this kind of thing so that the heel of my hand doesn't hit. Yeah, let me try that real quick if you don't mind. I'm going to go ahead and put the heel of this thing on and see if that doesn't work out a little bit better. Yeah, so this is a very weird looking glove, but it keeps, hopefully it'll keep that thing from happening. Okay, all right, so plus the limit is x approaches 3 of x cubed. Now there's some other limit, there's other limit definitions too, right? That you can move exponents around, and the limit of a product is the product of the limits and those kinds of things. So what I can actually do is I can say, well, x is equal to 3, and so I can just plug this in because I know the value of x is the function is continuous for all values of x, right? So I can put 3 just for that. But what I can do here is I can say, hey, this is the limit as x approaches 3 of x, which I've already found out, and then I can square that limit number, right? So the limit of a power is the power of the limit. Same is true for any real number power, right? So I can do that whole limit cubed. And so I already know that this limit is 3, right? So this is going to be 3 squared, and this is going to be 3 cubed. And you might be saying, hey, Mr. Molekash, why are you going to all this trouble? What's the deal here, right? Why are you writing all this crazy stuff down? Because you can not just assume that you can plug the number in and get the value of the limit, right? Evaluating a function, we talked a lot about this last week, evaluating a function is not the same as evaluating a limit. So you have to be a little bit careful and deliberate and use these theorems, okay? Use these theorems. I got to be careful not to press buttons here. But use these theorems to evaluate limits. So I would encourage you to kind of get familiar with what's going on here. Why does it say provided L2 is not equal to 0? Because of course you can't divide by 0, right? So if the limit of g of x evaluated there is 0, then you're not going to be able to divide anything by 0. Okay? All right. Let's see if it will let me scroll. Yay, check that out. I can scroll with my pen. I'm figuring this out. So there's a neat little example here of what they do. Like they can multiply by 7, they can square the limit, and we know the limit here is x naught, and we know, or x sub 0, and we know the limit there is x sub 0, and so yeah, they kind of use that same idea. Okay. I wish it would scroll the other way, but it's okay. I'm not going to complain. All right, so real quick, last week also we talked a little bit about left and right hand limits. And so in this picture, let's see if I can get over here and get to my pen again. In this picture, what we can say about this apparently that didn't work out. I got to be careful how I use this thing. All right, in this picture, what I can say is the limit as x approaches x sub 0 from the left of f of x is equal to something. Look at that picture and tell me what the answer to that is, or at least think about it while I'm writing the right-handed limit down. See if you can think about that. Okay. All right, so over here, if we're approaching from the left, it looks like the first left-handed limit is y sub 0. Okay, so remember, it's almost as if you can't even see the right side. Over, you're approaching the x value from the right, and that y value is getting very close to y subscript 1. Okay, now when this kind of thing happens, there is a what we call a jump discontinuity. And sometimes we can say that this is non-removable. This is non-removable. So from this prior week's lab, this is an example of a non-removable discontinuity. And that happens in limits when the limit from the left and the limit from the right are not equal. So there's a little bit more to the story with continuity, but when this kind of thing happens, the discontinuity is so bad that you can't just fill in a y value and make the function continuous. Okay? All right. I'm going to try to do this tool without screwing this up. You guys are doing a good job being patient with me, but here's an idea of left and right-handed limits using epsilons and deltas, and there's an example here. Okay. I want to definitely talk about limits at plus and minus infinity. Let me give you an example of that. So let's say that we had, whoops, here we go again, I got stuck. So I'm so sorry, you guys. I need to be really careful about the buttons that I press here. Let's say that x is approaching infinity of 1 over x plus 2. And let's explore this by using a table of values, right? So we have x, and then we have f of x, which is 1 over x plus 2. And since x is approaching positive infinity, what we need to do here in our table is we need to get numbers that are getting increasingly large very fast, right? So maybe x starts out being 1, and then it goes to 100, and then maybe 10,000, and then maybe 10 to the 6th power or something, a million, right? So what happens when we put 1 in this? We get 1/3. If we put 100 in here, we get 1 over 102. And so the denominator is always going to be the x value plus 2, right? So the bigger the denominator gets, I'm going to try to actually write out all those digits here, 1,000,002. As this gets bigger and bigger and bigger, we say it approaches infinity. Now, infinity is not a number. You cannot put infinity in the place of x. Don't do it. It's just not a thing, right? That's why we write approaches infinity. X can never equal infinity. Infinity is not a number. That's a dangerous thing. Don't do it. But as x approaches infinity, what do you think these numbers are getting closer and closer to? Maybe using a calculator might help, right? So if I brought out my calculator, 1/3 is 0.333. This would be 0.09 something, right? Something like that. Actually, 009, right? So it's a really small number. And then this is even smaller and this is even smaller. But how small can it possibly ever get? What limit does it reach? And it certainly looks like that we're approaching 0. So we can informally observe from this table that the value is 0, right? Okay. Another thing we can do, let me kind of hide all that and come and just very quickly look at Desmos graphing calculator, right? So DES. What's happening to the graph of 1 over x plus 2? Right, so at 1 we definitely got 1/3, right? 0.3 repeating. At 10 it was small number. I got that wrong. It was 0.083, not 0.09 or anything, so I definitely had the decimal wrong. But you can observe, right, as you get increasingly large values of x, look at what's happening to the y values. They are getting very, very close, very, very close to the x-axis. And the y value of the x-axis, of course, is 0, right? So that's the kind of observation that we're making. So in this section, what they're saying is, here is that we need, as x approaches if the limit as x approaches infinity is equal to something, some limit, then there's a horizontal asymptote on the graph. And you're familiar with that before, right? So we saw that in Desmos just a little while ago up here, right? So that we're approaching a horizontal asymptote of some sort. Like the function y equals 1 over x has a horizontal asymptote on the right side of x equals 0. Okay, so there's a wonderful delta epsilon explanation of this. Now, thank God there's a way of dealing with this kind of thing without using epsilons and deltas. And what I want to do is kind of flesh this out over here a little bit. You're going to have to do this in this week's lab, so pay close attention. If you're doing, say, the limit as x approaches infinity of 2x cubed minus 7x plus 2 divided by, maybe you remember your math teacher, maybe in high school, maybe in an earlier math course, saying, hey, that x cubed and that x cubed are the same, so the answer is going to be 2 over 4, right? Which reduces to 1/2. So that is the informal, quick, cheap, easy way of getting the answer, okay? What I need you to do to show your algebraic work, algebraically, okay? You cannot write this down and get full credit. This is what you have to do, okay? We're going to divide the numerator and denominator by x cubed, which is the highest power of x that appears in the rational function. So the highest power of x is x cubed, but what I'm going to do for you is I'm going to rewrite this exact problem all over again, but I'm going to leave space after every term, and you'll see why in a moment. Oh, I got away with it that time. 4x cubed plus 7. Okay, so let's pretend that this is a fraction bar. Alright, so let me go change colors here. And what we're going to do is we're going to multiply every single term here by 1 over x cubed. And this is a legal operation, because remember, x is not equal to infinity. So I'm not multiplying or dividing by 0 anywhere. This is okay. This is totally legal. Okay. All right. Now, by doing that, let's see if we can simplify what's here, okay? So obviously, x cubed divided by itself is definitely 1. So the first thing we get is 2. So that turns out to be 2. What does this turn out to be? Well, the x and the x cubed reduce, and we get 7 over x squared. Okay, you're starting to see this over here, right? So they write 7 times 1 over x squared and move the 7 in front of the limit. But trying to simplify this process for you a little bit. Okay, uh-oh, happened again, sorry. All right, so this next part turns out to be 4, and then this next part turns out to be 7 over x cubed. Okay, now what can be done is that you take the limit of each of these individually, and we have the right to do that because of theorem 1, right? Which means, you know, the sum of the limits is the limit of a sum is the sum of the limits. The limit of a product is the product of the limits. We have the limit of this complicated expression, but we can take the limit of each part individually and then calculate the math with the limiting values, right? So very technically, right, this is the limit as x approaches infinity of the number 2 minus 7 times the limit as x approaches infinity of 1 over x squared, right? Because 1 over x squared is, I could just do the 1 over x and then square the whole thing, right? I can do that. And then I can also do 2 times, this is very technical, okay? And in practice, in most calculus, you won't ever have to write this out, but you have to know that this is the operations these are the operations that are going on, okay? This is what you're actually doing when you're finding a limit. You're actually doing all this. This is the stuff that's going on under the hood of the car. So calculus is very, very, very powerful mathematics, and we have to treat it with great respect. Okay, we can put the 7 in front of that. So 7 is multiplied technically by 1. So I can do 7 times the value of the limit, and that limit is cubed, right? Now, let me ask you, what is the value of this? Whoops, my pen is not working. Okay, what is the value of that limit? What is that limit by itself? You see that keeps going up over and over and over and over again, and we saw it earlier in the textbook, right? It's 0. So what I can do for all these little pink things is put 0. Now the limit of a constant is the constant, right? The function y equals 2, even out as we approach infinity, is still going to maintain the y value of 2, right? All the way across. So this limit is 2 minus 7 times this limit is 0 plus 2 times this limit is, well, also 0, and we get to raise that to the 3rd power. And then what's this limit right here? This is 4, because like we said, the limit of a constant is the constant. And then 7 times 0 cubed, right? So what we finally come out with is 2 minus 0 plus 0 over 4 plus 0, which really is 2 over 4. So maybe in your pre-calculus classes, when you're finding the value of a horizontal asymptote, and it just turns out to be 1/2, you weren't really calling it limits. This is what you were doing. You were just comparing the coefficients. But really, what was really happening to justify the fact that there's a horizontal asymptote is this, okay? So this function right here, if you were to graph it, it would have a horizontal asymptote at y equals 1/2, okay? And so we see that down here. All right. So I thought I would just take a little bit of time and explain this because, like I said, you're going to have to do this process in Lab 1.2. Okay, you have to show that we're multiplying every single individual term by 1 over the highest power, and that those limits that are 1 over x, they all go to 0. And then you can put in 0 for the value of the limit, and then you can calculate the values from there. Okay. You're not going to have to do this every week. This is a very slow and painful process, but you will get through it. I promise. You will get through it. All right. Let's see if I can get back to blue. How's blue? I think blue's a little bit better. What do you think? Okay. So, what happens when x is a number? Let's say we have 3. What happens when x is a number and we approach that number from one side and we get infinity? Like, what does that mean? What does that mean? What that means is that, and in the question here they're using 2, what that means is that as we're approaching in a graph setting, okay, let me switch colors now. What that means is that around y equals 3, on the left side of 3, the y values are so big that something like this is happening. What am I drawing here? What kind of thing is this? We call this a vertical asymptote, right? So that means if instead of x approaching infinity, if the answer is approaching infinity, it means you have a vertical asymptote. Okay, so let's kind of summarize this in a table. If x is approaching a number and f of x, and this would have to be from one side, right? And f of x is approaching infinity, then we have a vertical asymptote. And this could be plus or minus. It can be one side or the other, right? Or even from both sides. Like you can have a function where it goes to positive infinity on both sides like that, right? Just depends on the function, okay? All right. Now, if x is approaching positive or negative infinity, whether it's the infinity on the left or the infinity on the right, and f of x is approaching a number, just say some constant, then that means we have a horizontal asymptote, right? That's what we were looking at up there. Now, what happens if they're both infinity? Like, what if x is approaching infinity and, f of x is approaching infinity? Well, that means that you have a function. That means you have a function that's, as you go off to the right, the function is going way up here. And you might have learned about that in a pre-calculus class. This is what you used to call end behavior, right? So this kind of thing is called end behavior. And end behavior in this sense, where both x and y are going infinitely large, is kind of like a polynomial, right? Like a parabola does that. As x gets positive infinity, y goes to positive infinity. So you may have been writing this in your Math 3 class in high school or in Math 171 or 172. This is not anything foreign to you. But what we're doing now is we're kind of formalizing this by putting limits in with it. Okay? So that's kind of what these unbounded functions are talking about. It means that as we're approaching x from one side, there's no boundary. There's no y value that we're approaching, okay? And that means we're getting a vertical asymptote. So with infinite limits, we have a vertical asymptote, right? If f increases or decreases without bound as x approaches x0 from either the left or the right, then the line x equals x sub 0 is a vertical asymptote. And so this is a formal definition of what a vertical asymptote is. It really has limits at its core. Okay, vertical asymptotes are limits, as are horizontal asymptotes. So again, we never learned it like this in pre-calculus because you weren't ready to learn this concept yet. Okay. All right. Limits with infinity, there's a little summary chart here of what you can do when you're dividing, right? So basically an infinite number divided by a constant is going to be infinitely large. Like an infinite amount of money divided by anything is still infinite, right? If the top number is finite and the bottom is infinite, then you're going to get 0. And so what this kind of represents is a horizontal asymptote. A horizontal asymptote at y equals 0. Okay. What's happening here is not a vertical asymptote. It just means that that when you're dividing the two functions, the quotient function is going to have something very, very large as we approach this value from the other side. So this could be a vertical asymptote at x equals x naught. Okay. And here, the absolute value deal, right? If the top is a limit and the bottom is getting very close to 0, then we're going to say that's infinitely large. And what that means is that the top numbers are getting really big, but the bottom numbers are getting really small. And as the top gets bigger and the bottom gets smaller, the fraction gets way bigger. Okay? So that's kind of like an observation about limits, and these are theorems that can be proved. Okay? All right. We're almost done, you guys. Thanks for hanging in there with me. I appreciate it. So here's some exercises that I want you to try after you've read the book again. Okay, and I want to talk to you a little bit about the next section, especially when it comes to something called the intermediate value theorem. All right, so what does it mean for a function to be continuous? Continuity revisited, right? So here's a couple of things to take away from this section 1.3. Definition 10 is very important. Very important. For a function to be continuous. So let's draw a picture for this. Right? Let's just say that there's an x sub 0, and we want the function to be continuous at this x value. So what that basically means is that when I draw the function, I don't have to pick up my pen, right? That there's some number here on the y-axis that's f of x sub 0, right? But it's not enough just to have that point listed there because, let's see, because what could happen is that you might have that point, but you might have something going on like this. Remember that from last week? That was a discontinuous function. In fact, this is a removable. So, just the fact that f is defined at x0, so f of x0 exists, in and of itself is needed, but not enough by itself. Okay, because you could have something like this. Now, the limit as x approaches x0 from either side exists, and this also is true, right? There's a limit here. So here, the limit as x approaches x sub 0 of my function is some number, which happens to be this horizontal line up here, right? But f of x sub 0 is not L. So we have the first two conditions, but the limit and the function value must also equal each other. So what happens is, if we remove this discontinuity and f of x sub 0 is equal to L, then guess what happens? We can say that our function is continuous, right? So we have a y value, which is L. We have a limiting value, which is also L. And so since they're both the same, then we can say that this function is continuous f of x is continuous at this x value, just at this one x value, okay? So this is really important that you understand the continuity of a function, because if a function is not continuous, then there are certain things that we can't do in calculus with those functions, right? You can't differentiate a function. You can't find the derivative at a place where there's no continuity. And then, you know, if a function is differentiable, it is automatically continuous. So there's something coming down the pipe here in Unit 2 that has to do with this. And again, this is super ultra important. You need to know this. Hint, hint, hint. All right? And the only other thing I wanted to talk to you about before we part ways, let me just switch to the mouse here, is the intermediate value theorem. This is coming in a future lab. So I'm going to try to scroll down here. Maybe. Intermediate value theorem. Okay. I want you to take a good look at this picture, and I want to kind of talk you through. This is the most common sense theorem I have ever learned in my life. And basically, we're going to read this down here in a little bit, but there it goes again. All right. Basically, what this is saying is that if f is a continuous function, so let f be continuous at all x values on the closed interval from a to b. Okay? Then there must exist, C, where C is between A and B, such that f of C is also between f of A and f of B. So if there's some number in here, then there's got to be at least one of these numbers where the y value is in here. Remember those two strips we talked about earlier, where like the x naught and all that kind of stuff was in a vertical strip, and the y f of x naught was in another strip? This is very similar to this, right? So if a function is continuous, if it doesn't have breaks in it, if it doesn't have asymptotes or holes or anything like that, then we can guarantee that there's at least one of these guys whose y value is between the y values of the endpoints of the interval. Okay? And let me erase all that off the picture, because there's an identical one or almost identical one to that right below here. Is this going to work out? Okay. So here it is in its textbook definition. Let f be continuous on the interval from a to b, closed interval, which means there has to be a point there and a point there, and a point there and a point there. Let L be a number between f of a and f of b. There exists at least one number c such that f of c is equal to L. Okay? So if f of c may not be between f of a and f of b, right? For all values. Let me just do this. So let's say that I drew a function like this. Okay, so here's A, here's B, here's f of A, here's f of b. So what happens if there's a point there and there's a point there, and I draw something weird like this? Okay. The theorem says pick any number you want in here. Any number you want. there's got to be at least one number whose y value has that as its y value. And in fact, there's a bunch of them, right? There's one there, there's one there, there's one there. So there's a C1, and there's a C2, and there's a C3. So the theorem guarantees that there is at least one number. In this kind of function, there's only one, right? The y values don't repeat. But you can imagine, like with the sine graph, if the interval's big enough, there's lots of c values, or the cosine graph, or any periodic function. So this is a really important theorem in calculus as well. It gets used a lot to develop further ideas when we get into derivatives and integrals. So it's very, very important launch point for some other stuff. And this is coming in Lab 1.3. So you definitely want to familiarize yourself with this theorem. And it's kind of like a common sense idea. It's kind of like, okay, if there's y values in here, then there's got to be at least one x value that has this y value. There's at least, but again, the function has to be continuous on a closed interval. This has to be true, otherwise the theorem doesn't apply. Okay, so just make sure that you're aware of that. All right, now finally, I want to take you to Blackboard and just kind of like go back to things that we've been doing. So there is a week 2 folder where this video is now. I want you to go back and reread sections 1, 2, and 1, 3 after this, and I apologize for how long this video was. Thanks for hanging in there with me. And post in the discussion board if you need help. I do have an Ask Mr. Molakash thing in there. I have email, so you can send me an email if you have a private question. And look, be proactive. Don't wait till the last minute. Calculus will eat you for breakfast if you wait till the last minute to do all this stuff. So slow and steady diet, slow and steady wins the race, just like the tortoise and the hare. So I hope you have a really good week. Please keep in touch with me. Let me know how you're doing. I'd love to hear from you. Talk to you soon.